All right. So, Assalamu alaikum, everyone. Uh, it's really nice to be back today and talk to you. So, today is going to be my last lecture in this really useful workshop. As one can imagine, there's a huge diversity of lectures here. Some very exciting and cutting edge topics are being covered. So, I hope it's all going really well. And it's a great privilege for me to be a part of this. So today in my talk, I'm going to talk about measurement-based quantum computing, but I'm also going to cover up some of the lost ground from the previous lectures. So I'm going to skim through two kinds of algorithms as well, the Deutsch algorithm and the Grover search algorithm. And I'm going to do that really quickly so that we also, I can also do justice to the topics that were assigned to me. And then we'll come up with this really interesting idea of measurement-based quantum computing, which is very much aligned with photonic quantum information processing, because photons give a really nice test bed for implementing measurement-based or cluster state or one-way quantum computing, as it is called. There is another lecture, I think tomorrow, the day after, on reservoir photonic quantum computing, and this is also related to that topic. So far, so good. I will now switch to my digital board. So please excuse me while I do that. I'll have to switch off my video. All right, so let me share my screen. Okay. All right, so I hope you can all see my screen here. So you've already looked at quantum algorithms. There has been a special session, I assume, yesterday on quantum algorithms. So a very quick recap of two important algorithms. So can you hear me clearly, and can you see the screen? Can anyone just point out? Can all right, so you can, all right, so that's fine. So excuse me.
No problem here.
Okay. So the Deutsch algorithm is a really nice algorithm in the sense that it demonstrates what an algorithm looks like, but for all practical purposes, it's a useless algorithm. But nevertheless, it has its pedagogical value. So the Deutsch algorithm basically, in its simplest form, takes 0 or 1, and we can define a function that acts on this single bit and makes this go into 0 or 1. So it's a kind of a benign function, not of much use. But suppose we have two kinds of functions. One is called a constant function, and the other is called a balanced function. A constant function f is such that when f acts on 0 or it acts on 1, you get the same result, either 0 or 1. And a balanced function means that f of 0 is not the same as f of 1. So there are two ways in which the function can be balanced. So f of 0 equals 0 and f of 1 equals 1 is one instance. The other instance is f of 0 equals 1 and f of 1 equals 0. And for constant, you can have the two scenarios that either both of these functions are equal to 0 or both of these functions are equal to 1. Now, if I give you the bits 0 and 1 and I ask you to determine whether the function is constant or balanced, you will take 0, apply f to it, and measure. And then you will take 1, apply f to it, and measure, and see whether the outcomes are identical or dissimilar. In the Deutsch algorithm, you can implement the function on a quantum computer and test whether the function is constant or balanced in one go, in a one shot measurement. So the circuit diagram for the Deutsch algorithm goes as follows. You have two qubits. Those two qubits are input, and you apply a Hadamard gate to each of the two qubits. And then you apply a function, UF, which implements, you apply a unitary gate, UF, that implements a function F. And how do you define UF? UF is defined in the following fashion. So let me define UF. So UF is defined such that if I have X, ket X in the first qubit and ket Y in the second qubit, the action of UF would be to keep the first qubit the same, and the second qubit gets a value which is equal to the exclusive OR of the contents of the second qubit plus the application of the function on the first qubit. For example, ket 0 would become 0, 0 exclusive OR. Ket 1, 0 or 1, 1 would become ket 1, 1 exclusive OR f of 1, etc. So the first qubit remains unchanged, but it controls what's going to happen in the second qubit. And the second qubit takes up a value which is the exclusive OR of the application of f on the contents of the first qubit and the original contents of the second qubit. And an exclusive OR is very simple. It's just defined as the output is 1 when the two input bits are dissimilar. Otherwise, the output is, this is the exclusive OR of X and F, X and Y. So this is how we define the exclusive OR. So let me kind of go back to my original. So this is the circuit here. This is the circuit here that implements the Deutsch algorithm given a certain input state. Suppose my first qubit is in the state ket 0 and the second qubit is in the state ket 1. The second qubit is an ancillary qubit. Since we're dealing with the application of functions on 1 bits, we really need 1 qubit, but the quantum algorithm necessitates the usage of an additional ancillary qubit. So both of these qubits are initialized and both of them see Hadamard gates. So if I progress through, if I kind of progress through from left to right, I propagate my quantum state. Let's see what's going to happen to the quantum states. So I start off with 0, 1, Hadamard gate on both the qubits. The Hadamard gate on the first qubit implements this superposition. On the second qubit, it implements another superposition with an opposite phase, and then I expand all of this. This is what I get. And then I implement the unitary operator that executes the function that I've described just now. So UF acts on this state here, and each of these component states inside the superposition, they see the application of UF. So as you can well imagine, the first term goes to 0, ket 0, and the second qubit becomes f of 0. The minus, all the minus and the pluses are preserved, and you repeatedly apply the unitary operation on each of these terms. And go forward from here. So in the next step, what I've done is I've factored out what happens to the second qubit. So the second qubit state is now written in the red brackets. So I have a superposition of two qubits. Here is the superposition. First qubit ket 0 tensored with the second qubit in this state, plus the first qubit ket 1 and the second qubit in this state. Now, depending upon what is the value of f of 0 and f of 1, I can generalize the state of the second qubit as 0 minus 1, but it can pick up a positive or a negative sign. And the positive or negative sign depends upon the values of f of 0 and f of 1. So let's suppose that f of 0 is 0, say. So this term would become 0 minus 1. And that's what I've written over here. Suppose, on the contrary, that f of 0 is 1. This term would then become ket 1 minus 0. Now, this scenario is captured in this exponent over here. So I put a minus 1 sign as a scalar coefficient and exponentiate that minus sign up to f of 0, the value of f of 0. So this can be positive or negative, depending upon the value of f of 0. Likewise, this term can be positive or negative, depending upon the value of f1. So this is really, really simple and really, really nice, really kind of intuitive. So then what happens is I apply, if I've redrawn the circuit over here, I apply another Hadamard gate to the second qubit. When I apply the Hadamard gate to the second qubit, this just collapses into ket 1 here, okay? And the first qubit becomes the superposition here. And the relative phases between the ket 0 and the ket 1 in the first term, they are defined by the values of f0 and f1. Now in the quantum circuit, I have a Hadamard gate on the first qubit. I can ignore the second qubit because I don't use it subsequently. I can now pay all my attention to the first qubit. So let's just look at the first qubit. If I just look at the first qubit and implement the Hadamard gate, ket 0 goes to 0 plus 1, ket 1 goes to 0 minus 1. Then I do the algebra, and the result is extremely, extremely simple. The result is that the term ket 0 picks up this phase. This number could be 0 or it could be 2. Ket 1 picks up this phase. This number could also be 0 or 2. But notice that we have a positive sign here and we have a negative sign here. So if this number is plus 2, this number becomes 0. If this number is 0, this number becomes plus minus 2, etc. Therefore, suppose the function is constant. Constant function means f of 0 equals f of 1. Now suppose this is 0. So what this means that the second term will disappear. This term is going to disappear and you'll be left with an output which is just ket 0. And it doesn't matter whether the function is 0 or it's 1. Whenever the function is constant, either of these two scenarios are applicable, but both of them will yield this result. If the function is balanced, the output from the quantum circuit will be ket 1. So what we've in effect done is we've built a circuit that implements an algorithm, the Deutsch algorithm in this case. We focus our attention on the first qubit, though we have to initialize the quantum computer in a manner that the two qubits are in well-defined states. We do a unitary process, a sequence of gates, and the sequence flows, the quantum state flows in time through this quantum circuit. And finally, you do a Hadamard on the final qubit and do some kind of measurement. And that measurement basically is choosing whether your output is ket 0 or your output is ket 1. So if you're talking about photons, then the you could use, say, different degrees of freedom. For example, you could use the path or you could use polarization. And if you're using the polarization, for example, the ket 0 and the ket 1 could correspond to horizontal and vertically polarized light. So, and the optical elements will be chosen accordingly. And you can have a polarizing beam splitter that takes an input and separates out the horizontal and the vertical photons, and then you detect. So now the collapse of the measurement is not a problem because we have designed our quantum algorithm in such a fashion that even though a superposition does exist inside the quantum computer, the final result, which is a choice between two possibilities, whether the function is constant or balanced, maps onto the two orthogonal states of a qubit. So this is how a quantum algorithm is really defined. And what we need to build a quantum computer is we need to initialize our qubits. We need to do some kind of unitary process. We need to measure. And if this quantum computing needs to be useful, it needs to be scalable. So if it's easy to build a 2-qubit quantum computer, it should be easy to build a 3-qubit and 4-qubit and so on. And the fifth is that all of this should happen so fast or in a manner that mitigates decoherence. Because your quantum states are kind of dephasing with time. They are interacting with the environment. Your pure states are going to turn into mixed states, and you want to avoid against that. So these are the 5 criteria that you need to have, generally called the DiVincenzo criteria, that one needs to satisfy in order to build a purposeful quantum computer. So this was my first example of a quantum algorithm. And now I would like to talk about another algorithm, the Grover search algorithm. So at this point, let me just pause a little bit so that I can take some feedback from you and I can see if there are any questions or because it's very hard to be remote and not to see the audience and see what's on their faces. But if there are any questions, so what I'm going to do next, I'm going to talk about Grover search, and then I'll move on to measurement-based quantum computing and explain what it means and how measurement-based quantum computing implements a Grover's search algorithm. So any questions about this, about quantum algorithms? I'll just pause for 30 seconds, 20 seconds, and see if there are any questions, and then I'll move on.
Hello, Professor Sabieh, can you hear me? Can you hear my voice? Yes, not.
Sorry?
Can you hear my voice clearly?
I can hear it, but not very clearly. But please go ahead.
I'll try to ask it. What I want to ask is that the the circuits we implemented is solving a binary classification problem where we have 0 and 1.
I'm sorry, can you please
Yeah.
come closer to the microphone somehow?
I'll ask my question differently. Wait a second, please. You should be able to hear me now, I guess.
Yes, better.
The circuit we implemented solves a binary classification problem, whether the function is constant or balanced. Can we increase the scope of this? I mean, for a n class classification where we try to classify the classify the issue as say balanced, constants, or maybe another types of functions.
Exactly, we can do that. So if instead of having 2 qubits, I can have n plus 1 qubits. So on each of the n qubits, there's one ancillary qubit and n qubits, and I can form a function on an n-bit string instead of just 1 qubit. So I can do exactly the same circuit with the Hadamard gate on each qubit, and then apply a unitary operator, which is doubly or triply or quadruply controlled by each of these qubits and affects the ancillary qubit. So I can expand the size or the dimensionality of this problem very easily. In fact, the Deutsch algorithm is a basic version of a quantum Fourier transform. The quantum Fourier transform can, in principle, act on multiple qubits. So yes, we can still have a binary question, but the size of the problem can be really large.
Yeah, I see. Thanks.
All right, so let's move on. Switch back to my board. Now, the Grover search algorithm is also a nice algorithm, and it's slightly more useful than the Deutsch algorithm. Now, in the Grover search algorithm, suppose you have a string of bits, and let's focus on 2 bits. So if I have 2 bits, the database will comprise these 4 strings. And suppose this is a string that I would like to search. This is my target. So classically, I would need at least 2 computations or 3 computations, 3 measurements in this database to kind of find out my target. So now we define a quantum algorithm called the Grover search algorithm, which helps us pick up the string that has been tagged already in one go. So the algorithm is designed such that if it computes the application of a function on a string, n-bit string x, and this gives me 0 or 1. It gives me 0 when my x is not the same as the string that I'm looking for, and it gives me 1 when my x is identical to my target. So this is what the algorithm does. So suppose I want to search from two bits. So I initialize those 2 bits in the form of qubits, cat 0, cat 0. And suppose my target is the state is the bit string 1, 1. So I need my quantum computer to do something differently if my string that is embedded inside the problem is 1, 1. So how do I do that? So in order to do that, I use a similar scheme to what I've used in the Deutsch algorithm. I have a 2-bit string, so I have 2 qubits, and on top of that, I add an ancillary qubit, and then I apply a Hadamard gate to each of the 3 qubits now. The ancillary qubit is initialized in the state cat 1. And then I implement my version of UF for the Grover search. Now, this circuit that we have over here is called a Toffoli gate. The Toffoli gate inverts the third qubit when the first 2 qubits, each one of them are in the state cat 1. So this is what the Toffoli gate does. So the string 1 is hardwired into UF. So the third qubit is kind of flipped when we have hit the string on the first 2 qubits. So now all of this determination or decision process could be done in one quantum algorithm. So how does the quantum state propagate in this circuit as we move from left to right in time? So this is our initial state. We apply Hadamard gates to each of the 3 qubits. The first 2 qubits are 0, 0, so you get an equal superposition of all 4 states with positive signs. But for the third qubit, you pick up a negative sign in the relative phase. And then I simply do an expansion of this term. I get this. And my Toffoli gate is now implemented. Here is my Toffoli gate. What the Toffoli gate does is that it flips the third qubit when the first 2 qubits are in the state cat 1. So this term will be flipped and it's going to show up here. This term is going to be flipped and it's going to show up here. And all these positive and negative signs are preserved. So the signs are really important because the signs carry relative phases, and that's where the real quantum computation is, in fact, taking place. Now, once the Toffoli gate has been implemented, I kind of just refactorize things. I separate out the third qubit, factorize it out from the state expression, and subsequently I ignore it. I don't look at it. Now, my first 2 qubits are in the superposition. And this is a superposition of all the 4 strings inside the database. But my target has picked up this sign, which is different from the others. So it's picked up a relative phase. So there is some kind of hidden identification, some fingerprint with the target state, which is still not yieldable, which is still not giving me a product because it's in a superposition. And if I were to measure the state, it's just going to collapse and the phase information is going to be deleted. So I need to now design an algorithm that picks up this term, which has a different phase amplitude. Now, how do I do that? I feed these 2 qubits now, which have been prepared in this state, into another quantum circuit. That quantum circuit is sometimes called a Grover iterator. A Grover iterator. What the Grover iterator does is that it implements this operation. It implements 2 times ket psi, bra psi, which is an operator. It's a projective operator minus identity, where this psi is defined as an equal superposition of all the basis states. For example, if we have 2 qubits, there will be 4 basis states. So psi will be, excuse me, a superposition of 0, 0, plus 0, 1, plus 1, 0, plus 1, 1, over under root 4, which is 2. So now we are inputting a quantum state, this one. This goes in here. This is going into the Grover iterator. So let's see what's the action of the Grover iterator on this input state. First of all, let's see what the Grover iterator generally does. The Grover iterator is defined in this fashion. So let's first of all kind of figure out what this term does. What does this projector do to any arbitrary input state? So, right. So suppose my arbitrary input state is just some superposition of all the basis states where Ci's are unknown probability amplitudes. They are complex numbers. And this is from Hoja Jehun's first lecture. This is an arbitrary pure quantum state for n qubits. So now if my projective operator acts on this state, let's see what I get. So I just do simple quantum mechanical calculations. So I calculate this probability amplitude first, this thing. This probability amplitude is, so this is my ket phi, and this is my bra psi, it's a superposition. So I take out the summation signs, preserve the amplitudes, and this is a Dirac delta function or a Kronecker delta function, delta ij, which is non-zero only when I equals j. So the i's can be taken away. The i's have to be equal to j. So I can suppress the I variable, and finally I will get, so this thing here is the sum of all the probability amplitudes. And the sum of all the probability amplitudes is, so if I take the average of all the probability amplitudes, this is the sum of all the probability amplitudes divided by the number of their number. So using this expression, this probability amplitude here becomes this. Now, what I could do now with what I've already derived, I can look at the Grover operator and see what happens when it acts on an arbitrary input state. So I now just perform my calculations. So 2 times this is simply this probability amplitude that we've derived over here, acting on psi minus phi. I just put in the values, all the values, simple algebra here, finally get this result. And at the very end, the action of the Grover operator on an arbitrary input state is this. Now, this is really, really, really interesting because the input state was Ci ket I sum over I, or let me write this again. This is my input state. Now, my output state after passing through the Grover iterator is the same basis states, but the amplitudes have now changed. The amplitudes instead of Ci are now twice the average of Ci minus Ci. So let's see what this happens to the specific case that we are discussing. This is our input state for the particular example that we're looking at. And these are the probability amplitudes. So the probability amplitudes, of course, all of this is with a factor of 1/2 for normalization. So the probability amplitudes are 1/2, 1/2, 1/2, and minus 1/2. So these are all the Ci's. Now, if I take the average of these Ci's, so I will get 1/4. Now, if I multiply the average of Ci's with 2 and subtract from this I will get all of the terms. So initially, my Ci's were half, 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 minus half. Okay, half, 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 minus half. Now my new probability amplitudes, each one of them is the following. So 2 times this is 1/2. From 1/2, I subtract the probability amplitude, I get 0, 0, 0, 0. And this is half minus 1/2, which is a probability amplitude of 1. So now when this circuit passes through the Grover iterator, my output state is ket 1, 1. And this is easy to detect because it's an eigenbasis of the measurement basis. So now what I've done is in one go, I can tell what my state is. I can look at my outputs and determine what the quantum state is. So if I go back to my quantum circuit for the Grover iterator, what's really happening is that at this point in time, I apply the Grover iterator, and my output state turns out to be cat1, cat1. So I can place detectors over here that can distinguish and determine what the output state is, and the output state is going to be cat1, 1. So in one go, by careful design and careful manipulation of the phases and the design of the Grover iterator, we can search for our target bit string. And this was the unique kind of genius, or I would say, the imaginative leap of Grover, who was able to define this Grover iterator. So for higher qubit states, Grover iterators exist, and sometimes you would need to apply them multiple number of times so that you kind of amplify the state that you're looking for. But for 2 qubits, just one application of the Grover iterator is sufficient. So now if you want to build the Grover iterator in terms of a quantum circuit, this is the circuit that one would have to build. So now this looks very unwieldy and very unprofessional, but this is what it really is. So in the earlier implementations of quantum computing, you started off with this very complicated quantum circuit. You had to fight against decoherence while all the unitary operators are being applied. You had to preserve the coherence of the quantum states as the quantum states progressed from left to right. So this part is what we've drawn above, and this part is the Grover iterator. Now, intuitively, why is this the Grover iterator? So let's focus on, first of all, what I've shown over here, just this part. if I notice carefully, there's a control NOT gate here. This is a control NOT gate. Okay. And when the control NOT gate is sandwiched between two Hadamard gates, it becomes a controlled phase gate. A controlled phase gate puts a negative sign on the second qubit if the first qubit is in the state cat1. That's what it does. So a controlled phase gate is very simple. It takes 0, 0, 0, 1, 1, 0, and preserves these states. 0, 0, 0, 1, 1, 0. And cat1, 1 picks up a phase -1. So this is what the controlled phase gate does. So this part is simply the controlled phase gate. Now I'm left with the controlled phase gate and two NOT gates over here. Now it's easy to kind of figure out what this circuit does. All of this circuit now implements this gate. And you can show this by explicit calculation. You can take the unitary operator for the NOT gate, which is an X gate, 0, 1, 1, 0, NOT gate, 0, 1, 1, 0. So this part is a matrix which is 0, 1, 1, 0, tensored with 0, 1, 1, 0, which is 0, 0, 0, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 0, 0, 0. And so is this. You can find out the matrix for this gate, which is 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, -1. And you can multiply the three matrices, and you'll find that this is equivalent to this gate. So what I've drawn in red here is this gate. Now, if I sandwich this between two additional Hadamard gates on each side, the 0, 0 will turn into an equal superposition, and this will become equal to 2 times ket psi bra psi minus identity, where psi is an equal superposition. So this circuit here, sorry, excuse me, this circuit here really does implement the Grover search process. Now, building all of these quantum gates is difficult. And so the main idea is that you initialize your qubits, you use a quantum circuit model, you have wires and you have logic gates, so unitary operators, adding different kinds of transformations to the qubits. You have a sequence of concatenated gates. You get an overall unitary operation, which is a reversible process. And at the end, you do a measurement. So it might be very unwieldy and inefficient and technologically difficult to implement all of these unitary operations. And the unitary operations are reversible. And the moment you get the environment into the picture, this reversibility vanishes. It goes away. So is there a way to kind of bypass this reversibility? Is there a way to bypass all of these unitary gates? And the answer lies in not having unitary gates whatsoever, rather using our measurements to perform a quantum computation. And that will be the second half of my lecture today. But at this juncture, let me kind of take a step back and take any questions that you may have. So I just need your kind of attention here if there are any questions about the Grover process. And I think I wanted to motivate, why do we need measurement-based quantum computation? Why is it so attractive? Why it has been so attractive? So any questions up to this point? So this is the traditional quantum circuit-based model of quantum information processing or quantum computing. And we'd like to now present an alternative paradigm, which is also about 10 or 15 years old. Still, it attracts a lot of attention, but it's an alternative and altogether alternative paradigm. There are other paradigms as well. One of them is adiabatic quantum computation. So there are different paradigms for implementing quantum information processes. So any questions? I'll just take a 20 seconds pause to see if there is anything you would like to interrogate me about. The form of oracle that you specified over here. Can you please come close to the microphone? The form of oracle you have used, for the two qubit system, not the gate. That's the oracle basically you are using, for the two qubit application, the Grover's algorithm. If you want to extend this to an n-qubit situation, how would you extend the oracle part only? The Grover iterator part? Yes, yes. You will have to design a new kind of Grover iterator, but still it's a combination of control knots, Toffoli gates perhaps. So if you just have the control knot gate, two qubit control knot gate, and an arbitrary Hadamard gate, a Hadamard gate, you can kind of construct all kinds of unitary gates because this combination of gates is universal. So you will just need a higher dimensionality, more gates would be needed. But in multidimensional systems, if you have more bits or more qubits, you would need a higher number of applications of the Grover iterator. In fact, there's a geometrical picture that you can find in textbooks that comes with the Grover algorithm, that you are searching for one particular direction. So you kind of move in that direction incrementally. So you need multiple applications of the Grover iterator. But for two qubits, just one iteration is enough. But the number of iterations that you need is not exponential. it's polynomial. And that's why this is a valid quantum algorithm. All right, so let me move on to the measurement-based. I would like to give you an idea of measurement-based quantum computing. So the key motivation is, let's not use unitary operators. So we have to sacrifice reversibility, which means that our quantum information processes become irreversible. That's why this kind of computation is called one-way quantum computing. And let's just use measurement outcomes, and see if through those measurements we can implement gates. We would like to achieve the same effect as the implementation of a computation, which is nothing but a gate or a unitary operation. So let's focus on measurements. Let's sacrifice reversibility. So we focus on measurements, we have to kind of put some energy somewhere else. That energy is spent on preparing the initial state. So you prepare an initial state appropriately, which is in most cases a highly entangled state. And that becomes a resource which is prepared offline before you start the computation. It's prepared offline, it becomes a resource, and then you just do measurements in a particular order, in a particular basis, repeated measurements, and their outcomes. If you get certain outcomes, you will be sure that you have implemented a certain unitary operation. So this is the basic idea of measurement-based quantum computation. So let me move on to the last part of this lecture and kind of see how the basic idea. I cannot go into lots of details, but just to give you the basic idea of how this is unfolds in reality. So just give me a second here. So okay, so I turn off my video. The same process again. I share my screen. All right. So in measurement-based quantum computing, it's useful to know what is teleportation. So I'm sure you've seen teleportation at some other point inside this workshop. But a quick recap is the teleportation of a single qubit is very, very simple. So you have a single qubit that you would like to teleport, and you prepare two additional qubits that are in an entangled state. For example, a Bell state, pi plus, which is a maximally entangled state. So the qubit you wish to teleport and one of the entangled pair, one of the photons in the entangled pair, they go to one party, Alice. So this is Alice's world here. And the third qubit, which is the second companion in the entangled pair, goes to Bob. So this is Bob's world. This is Bob. Bob lives here. Alice lives here. So what Alice does is she does a control knot on her qubits, followed by a Hadamard gate on the first qubit. So she really does a Bell state measurement on her two qubits. One of those qubits is in an arbitrary state alpha ket 0 plus beta ket 1. And the other qubit is one companion entangled pair. So then Alice does a measurement. So she has detectors, possibly single photon detectors, and she does a measurement. And she gets certain outcomes. So on each detector, she gets 0 or 1. 0 or 1. So there are four possibilities: 0, 0, 0, 1, 1, 0, 1, 1. So whatever outcome she gets, she then transmits to Bob over a classical channel. Phone call, fax machine, telephone, email, So, and what Bob does, Bob measures the two bits that Alice has transmitted, and based upon what outcome he receives, he applies one of four gates. He either keeps his qubit as it is, he does nothing. He applies an X gate, which is a poly X gate, a Y gate, or a Z gate. So he applies either nothing or one of the three poly gates to his qubits. And this is known in advance that if you receive 0, 0, this is the gate that I will implement. So Bob just applies a local gate on his qubit, depending upon the classical message that he receives. So what happens is that Bob's qubit, he hasn't measured his qubit as yet, but Bob's qubit after the application of this local gate is going to be an exact replica of the original qubit. So this is going to be the same, identical to this qubit. And no measurement has yet taken place of this final qubit, but this qubit is an exact copy of the qubit that one wishes to teleport. So now this kind of scheme of teleportation became the progenitor or the prelude to measurement-based quantum computation, and all the ingredients are already in here. For example, there is a measurement that takes place here. It's a classical measurement. That measurement is then transmitted, and the second party, Bob, just has to apply a local gate. And before the application of the local gate, here, the qubit. So suppose this local gate is U. Before the application of the local gate, Bob's qubit is U inverse of psi. After a message is received, this gate is implemented. So all the ingredients are already there for measurement-based quantum computing. So let me kind of do a step-by-step progression of this idea and see how measurement-based quantum computers can be implemented, or they can be designed. So the first thing that we need to remember is a few identities. Or formulas, which come in really handy. First of all, we are reminded that every unitary operator on a single qubit can be expressed as a rotation. So single qubit unitary operators are rotations on the Bloch sphere. An X qubit, an X operator or poly X gate is really a pi rotation about the x-axis on the Bloch sphere. And I'm sure you've seen Bloch spheres. So if I draw a Bloch sphere and I take the x-axis, then the X gate is really a pi rotation about the block, about the x-axis. So it takes a state that is here. You go around the Bloch sphere, the large circle on the Bloch sphere, and end up here. And this X becomes your axis of rotation. So this is what an X gate is. And if I would like to write down the matrix for an X gate, it's simply exponent minus I. The amount of rotation is pi. And since it's an X gate, I take sigma X, the poly matrix, and I divide by 2. And this division by 2 is because the magnetic quantum number associated with this system is 2. It's a qubit, it's a 2-level quantum system. So it is acting like a fictitious spin half particle. So likewise, you can define a Y gate, a Z gate, and so on. So each of these poly gates is a pi rotation about some axis. You can also have, so if I use this notation, X as a function of B, this means the a rotation through an angle of beta. Okay. So an x without any argument is really an x and pi with an argument pi. Okay, so this is the notation that I'm going to use. All right, so far so good. So any rotation. So if I draw the block sphere again, my rotation can actually be about any axis, n, which is defined by some angle theta and some azimuthal angle phi. So I can really have a rotation about the angle, about an axis that is oriented arbitrarily on the block sphere, and I can have a rotation about any angle. So I need an amount of rotation and the axis of rotation. So suppose my amount of rotation is a radians. So any rotation about the axis n through an angle a, in matrix form, it's going to be exponent minus iota a. And for the axis of rotation, I would need cosine theta sigma z over 2 plus sine theta cosine phi sigma x over 2 plus sine theta sine phi sigma y over 2. So this is the rotation in matrix form. Okay, but it's also possible to use your knowledge of classical mechanics to express this rotation r n a through three consecutive rotations, one about the z-axis through an angle alpha, followed by one around the x-axis through an angle beta, followed by a rotation about the z-axis through an angle gamma. So remember, when I write out unitary operators in this fashion, time is flowing from right to left. And if I were to draw this diagrammatically in terms of a quantum circuit, this will be a z alpha operation followed by an x beta operation followed by a z gamma operation. So this is my kind of ordering convention. So what does this mean? What does this expression mean? This expression means that any single qubit operation can be expressed as an x rotation sandwiched by two z rotations with the proper angles alpha, beta, and gamma, which are related to a and n. In fact, this is a nice homework problem. How do we, if we know n and a, or we want to implement a certain rotation, what should be the values of alpha, beta, and gamma? Okay. By the way, those who know mechanics, they would recognize that alpha, beta, and gamma are sometimes called the Euler angles. Right? So any rotation operator can be expressed in terms of these x and z operations on a single qubit. Now there are two or three more identities that are really useful. One is a z operation through pi. Of course, when I don't write an argument, it means pi, but I can also have an argument. But in general, z operation followed by a Hadamard gate equals a Hadamard gate followed by an x gate. This is another identity. All right, and you can prove this by explicit calculation. What this also shows us is that x will be equal to hzh. Okay, so if I multiply this right hand side on the right, sorry, excuse me, sorry, excuse me, just a minute. My screen has just stopped sharing. Let me share again. Okay, so I'm just having some problems with my software. Okay. All right. So I can modify this as HZH. If I multiply on the right by another Hadamard, I know that the two Hadamard gates in close succession are identity. The Hadamard is self-inverse, so this is X. All right. So what this means is that my arbitrary rotation, which was which was Z X Z alpha beta gamma, I can express this as, I can pre-multiply with two Hadamards. I can replace X by this H Z beta H, and just write this down here as Z alpha. Okay. So my ZXZ is really equal to this. So now if I make this into pairs, so this is one pair, another pair, another pair, followed by a Hadamard gate. So if I want to draw a diagram for this, first of all, I have this operation on the right in the operator form. So Z followed by H. So in a box, I can write this as HZ alpha, followed by HZ beta, followed by HZ gamma, followed by a Hadamard. So this is an arbitrary rotation. So the arbitrary rotation has been decomposed into Hadamard followed by a a Z rotation followed by a Hadamard, Z rotation followed by a Hadamard, Z rotation followed by a Hadamard, and an arbitrary Hadamard at the end. So what we've done is kind of converted this arbitrary one qubit rotation into a sequence of Hadamards and Z gates. So far, so good. So how do we implement these gates? So if you want to implement R, you would like to implement this gate, this gate, this gate, and a Hadamard. So we really want to have some mechanism of implementing Z, any angle, followed by a Hadamard. Now, if you look at our discussion of Hadamards, Hadamards are really doing some kind of measurement. So if you look at your Grover search algorithm, for example, all right, so here, so if you notice, or let's be very simple. Let's look at the simple example of the Deutsch algorithm. Look at this gate. What this gate is doing is that it's, if you had a superposition over here, this superposition is being projected back into the eigenbasis of the measurement operator. So the Hadamard gate is just, in a sense, taking you from the superposition basis or from the kind of superposition to an eigenbasis or a computational basis so that you can do a measurement. And a Z gate is simply a rotation about the Z axis. So a Z gate followed by an H gate is just defining a basis of measurement. So each one of these gates is just defining a basis of measurement. What is the measurement basis that you would like to choose? Along what axis would you like to make a measurement? Suppose if I look at the block sphere picture and I have a quantum state and I want to measure it. And this is my computational basis cat 0 and 1. So what you would do is you would just take this state, move it back to the computational basis, through the application of a Hadamard gate, and you'll get ket 0. If your initial state were on this side, applying the Hadamard will take you here. So you will get ket 1. So if your state is ket plus, the Hadamard will take it back to ket 0. If your state is ket minus, the Hadamard will take you to ket 1. And these are the two distinguishable states that can be discerned in a measurement. So the Hadamard gate is really taking your states to the measurement basis. And if that Hadamard gate is preceded by a Z gate, it really means that before you do a measurement, you just kind of switch the state, or the block sphere kind of twists back along the Z axis. So when you do that twisting, this state has kind of shifted back along the azimuthal plane or the equatorial plane, and then you follow it by a Hadamard. So in effect, you're just changing the measurement basis through the application of a Z and an H. So Z and H followed by an appropriate measurement, Z, H followed by a detector, is the same as doing a measurement in a tilted basis. And we can call that measurement B theta. So you rotate your block sphere about the Z-axis, and then you project onto the measurement basis. This is what in effect is happening. So now let's kind of move on a little bit and kind of use the teleportation example to kind of build up a scheme for measurement-based quantum computing. So if I were to kind of design a new circuit, and this kind of trick is called the 1-bit teleportation trick. This word trick has actually stuck to this paradigm, and this paradigm was proposed by Daniel Gottesman and Isaac Chuang. Chuang is the same author who with Mike Nielsen has written that famous compendium on quantum information and quantum computing. So what is the 1-bit teleportation trick? Sorry. Excuse me. So suppose I have this circuit, control not, Hadamard. Now this is the same circuit that we've drawn for teleportation on the first 2 qubits. So this is the same circuit that we have over here, this thing. Okay, so I draw the same circuit here. Now my first qubit is in any state psi. My second qubit is this. Okay, so my psi could be A ket 0 plus B ket 1. So here my input is really A 0 0 plus B 1 0. The first control not gives me 0 0 plus B 1 1. And then a Hadamard gate on the first qubit yields A over under root 2, 0 plus 1 0 plus B over under root 2, 0 minus 1 ket 1. Now kind of we just expand this 1 over under root 2 A 0 0 plus A 1 0 plus B 0 1 minus B 1 1. Now this I can write as 1 over under root 2 ket 0 tensored with, so I take this term and I take this term, A 0 plus B 1 plus ket 1, and I take this term and this term together, A0 minus B1. All right, so this is the state that I have achieved over here. Now, if you look at this expression here, let's look at this expression. The first qubit has a 50% probability of being detected in the state ket 0 and a 50% probability of being detected in the state 1. So if I were to do a measurement over here, and let's represent that measurement through a meter, M, whose outcome is M, and this M could be 0 or 1. So if my M output is 0, I have kind of collapsed my superposition into this state. And if my output is 1, my M is 1, I have collapsed into this state. If my output is 0, then the qubit here is going to be a replica of psi. If my output is ket 1, this thing, my qubit here is going to be this, which is an application of a Z gate on the first qubit. So this is a phase rotation on the first qubit. So what have I really done? It's really, really simple. This circuit, NOT gate, Hadamard gate, outcome M. So once I've done this measurement, so I have to wait for the measurement to take place. So once the measurement outcome is available to us, my output on this qubit is going to be Z raised per M psi. If M is 0, I have psi. And if my M is 1, I have the Z operator acting on psi, which gives me A0 minus B1. So this is the state if my outcome is 1, and if my M outcome is 0, my output state is A0 plus B1, which is the same as psi. So what I've really, really done is I've taken this measurement outcome. I get knowledge of this measurement outcome. And when I get knowledge of this measurement outcome, I have, in some cases, I would know, and that's going to happen 50% of the times, I would know that I have applied a Z gate. Now let's try to simplify the circuit a little bit. I know that a controlled NOT gate can be written as a controlled phase gate, which I've shown already, Hadamard. So Hadamard, measurement, M.
Hello, Professor Sabieh.
Yes.
It is lunchtime over here. Shall we continue to the measurement-based quantum computing in the next session that you'll have?
So this is my last session.
Or this is your last session? Because
Yeah.
1 p.m. over here, so the lunchtime
Okay.
about
So how long? I would just need another, say, 15 minutes.
Okay, 15 minutes I think should be okay. The lunch I think should be served after 15 minutes.
Okay, I'll just take 15 more minutes. I'll just wrap up. So we're very close to wrapping up.
Yes, this is actually a very good, an interesting point that you are explaining. We'd like to have it in detail.
Okay,
Actually.
I'll just take 15 minutes.
Okay, thank you.
And I'll try to be concise. So so this is psi ket 0. Now, if I simplify this a bit further, I have psi, and I can replace this Hadamard. I can I kind of get rid of this Hadamard if I were to replace this ket 0 with a superposition of 0 and 1. So if my input, instead of being cat 0, if I were to replace this with a superposition, I can get rid of this Hadamard. I still have a controlled phase gate, Hadamard, and Hadamard here, measurement. So this is still X, sorry, I'm sorry. Here I still have the state ZM psi. Now what I could do, I could move further, Hadamard, measurement, and kind of get rid of this Hadamard and have this replaced by ZM H psi. Okay, so I can just put this H together with this ZM. Now, another interesting thing could be done is that if I were to add another gate onto this input branch, Z alpha, Hadamard, measurement, then now instead of psi, the effect would be that I would have to replace my psi with psi Z alpha. And by the way, HZ here can be replaced by HXM, where X is the Pauli operator. And this comes from the identity that we have written at the top. So which is, and that identity is HZ equals XH. So I can replace this HZ with XH. In the next step, I've introduced this Z operator. So instead of psi, I have psi Z, and I just write down this here, H X M. So in the last stage, so this is just the last stage. In the last stage, I know that this is an operator that acts in the computational basis and it commutes with the Z operator. So I can take this operation and move it forward. When I move this forward, I get this configuration. Psi cat plus. Now Z followed by H. Measurement. And here I have H Z alpha XM psi. This we all know is just a measurement. We all know that this is just a measurement, B alpha. So you measure in a particular basis and your outcome is some kind of unitary operation acting locally on your qubit. So what you really need to do, if you would like to do an arbitrary rotation of this kind, you would need an HZ alpha, HZ beta, HZ gamma, followed by an H. And the manner in which you can achieve this really is through a circuit of this kind. And this is just going to be my last point over here. So if you want to do an arbitrary rotation, you build a circuit of this kind. Psi, the state on which you would like to implement a unitary operation, 3 additional qubits, each one of them prepared in a superposition, controlled phase gates on pairs, measurement on the first qubit B1 along alpha, you get some output K, measurement on the second qubit, B2 beta, you get some outcome L. Each of these K's and L's can be 0 or 1. Measurement on the third qubit about some axis gamma, you get some output M. And then you supply these values of L, K, and M, K, L, and M, these bits to this, the holder of this qubit, to this party. And based upon these outcomes, this party will implement some kind of unitary operation locally, and we'll find out that this qubit is going to be an arbitrary rotation about the first qubit. So by merely doing measurements across appropriate bases, by choosing alpha, beta, and gamma, you're able to do a quantum computing. And this is how you will actually be able to build complicated circuits like the Grover search algorithm. So the idea is to create a sequence of input states which are mutually entangled and then do measurements. So the sequence of input states is generally called a cluster. For example, I can draw a few clusters, few example clusters. So if I have these 4 physical qubits, I kind of initialize each one of them in the state ket plus. And then whenever there is a bond between 2 qubits, 1, 2, 3, 4, there's a bond between 1 and 2, 2 and 3, 3 and 4. I do a controlled phase between 1 and 2, a controlled phase between 2 and 3, a controlled phase between 3 and 4. This generates some input state. I then feed in this large input state into a sequence of measurements, just measurements, K, L, M, N, and so on. And I then look at the outcomes of these measurements. If these outcomes are specific and I have another qubit, then the state of this qubit will simply be a unitary operation acting on the input state. So this is a kind of what we call, sorry. I'm sorry. This is what we call a cluster state. So you generate your physical qubits, you initialize them in a superposition state, and then do controlled gates between those qubits. For example, if I were to start off in this state and I were to do a controlled gate, one will notice that I will get an entangled state. So what the initial state is, in general, a highly entangled quantum state. I can have cluster states that are linear. I can have cluster states of this kind, 1, 2, 3, 4, in which there's a controlled phase between 1 and 2, 2 and 3, 3 and 4, but no controlled phase between 4 and 1. I can first do a measurement on these qubits. The outcomes of those measurements will then determine what happens to the other 4 qubits, and then I progress along this cluster. I can also have a cluster of this kind, 1, 2, 3, 4. I can have more complicated clusters. So the basic idea is to generate these cluster states and finally do measurements. And through pure measurements, we can implement certain kinds of gates and implement certain kinds of algorithms. So now we're short of time, and this is lunch time, and I don't want to stand between you and lunch. I will share with Ozuan a few papers and some of my notes. that can help you take this concept a bit further. It will always be nice to do some computational exercise to kind of bring home this idea of cluster state quantum computing. It's a really, really nice idea. And I think a subsequent lecture on reservoir based photonic quantum computing will also be kind of related to this. So I would like to thank you.